Hello there. This is a special bonus video in which I'm going to do an example problem with you. I mentioned that I would do this in the video lecture I sent out yesterday, and I want to do an example problem in which you calculate the potential difference between 2 points if you already know the electric field that has been created by some kind of charge distribution. Okay? Finding delta V if you already know E. And so here's the scenario. We have a sphere. It's got a radius big R. It has a positive charge big Q uniformly distributed throughout its volume. And it's represented in the sketch here below. Okay? That's an actual physical sphere that you could touch. It must be a non-conducting sphere because it has charge throughout its volume. And it's got a radius big R and a total positive charge big Q distributed uniformly throughout the volume of radius big R. That means that charge distribution creates electric field everywhere throughout space, absolutely everywhere. And we should be able to calculate that electric field. That is to say, write down the symbolic formula for the electric field at any given location. Okay? Do you know how we would do that? Think about that for just a minute. How would we find the electric field anywhere for this, hint, spherical charge distribution? What method? Did you say Gauss's law? When you've got a spherical charge distribution, Gauss is one of the first people you want to go to because that's a very symmetric charge distribution. And sure enough, in chapter 23, we talked about finding the electric field of a spherical charge distribution. So this problem is assuming that we already know how to find E, since that was the topic of the previous chapter. So this is an example of what I mean when I say we already know E. Well, we already know how to find it. This might be how you would think about it. And given that we already know how to find E for this charge distribution, we should do so. And once we do, then we can use that knowledge of E, the electric field, to do the calculation that this problem asks for. Here's what it says. There are 2 points in space. They're labeled A and B. You can see them in the picture. Point A is on a 45-degree line from due right, and it is at a radial distance from the center, little r sub A, that happens to equal half of big R. Right? So that means this distance right here, from the point labeled A to the very center of that sphere, that's r sub A, that happens to be half of big R. That's point A, right down in that sphere. Point B, you can see, is also there, and it has a certain radial distance from the center of the sphere, straight out like that. And that distance is labeled little r sub B. And we are told that that distance happens to be 3 times big R. So clearly point B is outside the sphere and point A is inside. Here's what we need to do. Compute the electrostatic potential difference, delta V, equal to VB minus VA. Note the order. Find that potential difference between points A and B. That is our task right there. Find that quantity. Symbolically, right? No numbers here, just symbols. All right, the first thing I urge you to do for practice is, using Gauss's law, find the electric field created by this spherical charge distribution. Okay? I'm going to write down what you get, because we've already talked about that in chapter 23. But you should try for practice. Okay? All right. From Gauss's law, find the the magnitude of the electric field everywhere. I'll tell you one thing we already know from symmetry, that we have a spherical charge distribution and that the charge of that object is positive. We know the direction of the electric field at any point. E arrow points radially away from the sphere's center at any given point. Radially away from the sphere's center. So, for example, at point A, the electric field vector created by this charge distribution at point A must point something like that. Electric field at point, that's just at point A, radially away from the center. At point B, the field must point something like that, yes? Radially away from the center. And then that's going to be true anywhere. Pick a point. The electric field vector will point radially away from the center of the sphere. And I'm going to write down now the formula for the magnitude. Now, it turns out that you want to divide all of space up into two regions here. You want to think about points inside the actual sphere. Okay? All points inside that sphere, and then all points outside. Okay? You have to break it up into those two regions, and you have to apply Gauss's law separately to each region. And then you can get a formula for the electric field magnitude in those regions. So I'm going to write down what you get. This is going to be E magnitude, which I'll just denote by the letter capital E. And it will be what's called a piecewise function, because it'll have two different expressions depending upon where you are located. If you are at any point inside the sphere, that's going to correspond to the distance little r being between 0 and big R, okay? And the result, which you would get from Gauss's law for the magnitude of the field, is the total charge of that sphere, big Q, over 4 pi epsilon 0, its actual radius, big R, cubed, times, upstairs, little r. That's the formula for the electric field magnitude at any point inside the sphere, up to and including the surface. And this magnitude, this magnitude function, I'm just going to denote as E1. E1 represents the field magnitude at any point inside the sphere. What do we get for the electric field magnitude at any point outside the sphere? That one's an easy one. Although you can use Gauss's law to get it, you can also use the shell theorems and collapse the whole sphere down to a point particle at its very center, and then the electric field of a point particle is the charge, big Q, over 4 pi epsilon 0 little r squared. So this is for any little r greater than or equal to big R, outside the sphere. And I'm going to call that function E2 for the field magnitude outside the sphere. So here's what I mean. We know E. You have to do Gauss's law problem to get it, but we know E. So now, how do I find the potential difference, delta V, between the point A and the point B? Okay? All right. So now we use this physics idea. The potential difference between 2 points, delta V, which in this case, the problem clearly states that it wants that order. The V at point B minus the V at point A. So think of A as the initial point and B as the final, right? Because delta always means final minus initial. And that will be the negative of the line integral from the initial point, A, to the final point, B, of the electric field dotted into a little tiny displacement ds along a path that we pick, okay? we pick a path from point A to point B to do this integral, which is called a line integral, E dot ds. And now I'm going to show you what path I'm going to pick. And here's my hint, my advice. Now that we know what we know about E, pick a path between A and B that does either one of two things. Either follows the direction of E exactly, or is exactly perpendicular to E. Why? Because then the E dot ds's along those two various options are easy. If you follow the direction of E exactly, then the E and the ds are parallel, and that makes the dot product easy. If you take a path that's perpendicular to E, then the E and the ds are perpendicular, and that dot product is 0. Okay? So the hope is, for whatever problem you have, going from the initial point A to the final point B, that you can pick a path, you can break it up into regions, right? And along that path, you're either parallel to E or perpendicular to E. And you might have part of the path where you're one kind of situation and part of the path where you're the other. And that's actually what's going to happen here. So let me try to draw it right down here. So here's the sphere. All right, that's just the center point. There's the point A at the 45-degree line, halfway out to the surface. And roughly, there's the point B line, due right from the center at a distance 3r. Here comes the path. We're going to start at A and end at B. Now remember, the electric field vector at any point points radially away from the center. So with that in mind, the first part of my path along A is going to be along a circular arc. Wow, what the heck am I doing? A circular arc of radius big R over 2. You see why I want to do that for that part? That gets me down to where I'm on the line towards B. And then I just go radially out from the center until I get to point B. Okay? So that's what I would call a radial part of the path. Now, notice something. Along the circular arc at any point, if I were to draw the electric field vector, like at the point, let me get rid of some of this stuff for just a moment. How about at the point right there on the circular arc? What's the direction of the electric field? Radially away from the center. But what's the direction of the ds I'm going to take? The little displacement step along the circular arc. Well, aren't those perpendicular? They are. So along the arc, we can say, no matter where you are on the arc, that the electric field and the little displacement you're about to take, E dot ds, will equal 0. Because the E and the ds are perpendicular, and the dot product of perpendicular vectors is 0. That means there is no contribution to this line integral for any part of the path that's on that circular arc. So now all I have to focus on is on the radial part. Okay? Along here, let's pick a point. How about right there? Then the electric field vector points radially away from the center. So there's the E. And the ds is also radially away, because as I travel out to point B, that's the direction I have to step. So the E and the ds are parallel. So when I think about doing the E dot ds, that part, I'm going to have magnitude E, magnitude of the little displacement ds, cosine of the angle between the E and ds, but they point in the same direction, 0 degrees. Cosine of 0 degrees, positive 1. So this is just magnitude E, and then for the magnitude of ds, just the size of the little step you're taking, since it's along a radial line, we're going to call that size dr, a tiny radial step. And that's what I use for E dot ds when I'm on the radial part, where I've just got to put in the appropriate E for the place I'm at. And there's no contribution to E dot ds along the circular arc. So now with all that in mind, for the path that we've chosen, we can go about calculating delta V between points A and B. That's going to be minus the integral of magnitude E dr. And where do I start? I start right here, because the circular arc gives me nothing, and I end at point B. But I'm integrating in terms of a little radial distance dr, so the limits have to be the radial values, radial distances, from the center. So what's the radial distance when I'm at that point right there? Right there. It is that distance. What is that distance? The radial distance for point A, right? So the lower limit is the radial distance for point A. And the ending point is out there at point B. So the ending limit is the radial distance when you're at point B. Now we've got to understand that what I got to substitute inside this integral right there, the integrand, the E magnitude, is the value of E at each location along that radial line as I take tiny steps from the first point to the ending point. But wait a minute. That radial path then has to be broken up into two parts. Because for the first part, from there to there, out to the surface of the sphere, I'm inside the sphere. And then for the second part, from there on out to B, I'm outside the sphere. And if I'm at a point inside the sphere, then the electric field expression I have to use is the one up here labeled E1. But if I'm at a point outside the sphere, then I have to use the electric field expression E2. So, and here's an important point coming up. For this integral along the radial line from RA to RB, I have to break it up into two parts. Starting at RA until I get to the surface of the sphere, that's at big R, in which case I'm inside, so the electric field function I have to use is E1. And then I pick up at the surface of the sphere, big R, and I go on out to point B. R sub B, because now I'm outside the sphere, so the electric field function I have to use is the one I was calling E2. This is a very important step, and it usually takes a little while to get used to it. That is to say, understanding that, you have to break up this radial integral into two separate integrals, corresponding to the part of the radial path that's inside the sphere and the part of the radial path that's outside. Because the electric field function is different inside versus outside. All right, so delta V equals. Now I'm going to put in the actual E1 function and the E2 function in these integrals. So minus integral from R sub A to big R, E1, okay? Q over 4 pi epsilon 0 big R cubed times little r times dr. That's the first integral. Then, next one, minus the integral from big R to RB, E2. Q over 4 pi epsilon 0 little r squared, d little r. Okay, I put in the function E1 and the function E2 that we would obtain from Gauss's law. All right, let me talk about what we do next. Well, this lower limit on the first integral is the radial distance of point A from the center. I already know what that is, big R over 2. And all this stuff that I'm highlighting now in yellow are constants that can be brought out front of that integral. In the second integral, the upper limit is the radial distance of point B from the center, but I already know what that is. 3 times big R. And now everything that I'm about to highlight in yellow is a constant that can be brought out front for that integral. Now be careful about what you can and can't bring out front. That's what you can bring out front. You cannot bring little r out front, and you can never bring the d anything, like in this case the d little r out front. Never, never, never. All right, now let's work on these integrals one by one. All right, so I have negative q over 4 pi epsilon 0 big R cubed, integral from big R over 2 to big R of little r dr. Then minus q over 4 pi epsilon 0, integral from big R to 3 times big R of d little r over little r squared. Now both of these integrals are easy to do. I'll write the second one like this. R to the minus 2 power dr. They're both, look at the patterns, of this form. Integral x to the n dx, which is the first integral you learn. X to the n plus 1 over n plus 1. Except the x is little r, and the n in the first integral is 1. And the n in the second integral is negative 2. Okay, so no problem. Now we use that integral expression and figure out each integral. Do them one by one and slowly. So negative q over 4 pi epsilon 0 big R cubed. Okay, then for the integral I get little r squared over 2. And then there are the limits. All right, then minus q over 4 pi epsilon 0. Okay, the second integral will be r to the minus 1 power over minus 1. That's this, minus 1 over r, between big R and 3 big R. All right, just keep doing the math. So let's see, delta V equals negative q over 8 pi epsilon 0 big R cubed. I brought that 1/2 there in with the 4, times big R squared minus big R squared over 4. And then let's see, for the next term I have 2 negatives multiplied together. So plus q over 4 pi epsilon 0 times 1 over 3 big R minus 1 over big R. Next thing I did in the first integral was factor a big R squared from the parentheses, and it goes out front upstairs. Then I'm left in the parentheses with just 1 minus 1/4. That's 3/4. Then plus q over, now let's factor a big R downstairs. And then what we have in the parentheses is 1/3 minus 1, which is 1/3 minus 3/3, which is negative 2/3. Now let's see if things simplify. R squared and R cubed will partially cancel. And what's left? Well, negative 3q over 32 pi epsilon 0 r minus, well, what I can do here is I can do that and that, leaving it 2. So minus q over 6 pi epsilon 0 r. And you can factor a negative q over, well, you can actually factor a 4 pi epsilon 0 r. And then you'll have 3 over 8 plus 2 over 3. I think that's right. Yep, that's right. And you can get a common denominator there. And when you do that, the thing in the quantity in the parentheses becomes 25 over 24. So your final answer is negative 25 over 24 times q over 4 pi epsilon 0 r. Note the negative sign. That's important. That means the potential at point B, the final point, is less than the potential at point A. Okay? And we have calculated the potential difference. Now let me just talk briefly with you about how you could do one more something, just a little variation on this problem that actually is quite useful. You can use this kind of technique to find an equation for the electric potential at any radial distance, I'll call it little r, from the center, assuming a reference point out at infinity where we will assume the potential is 0. So for example, let me draw the sphere again with its center. I'll pick any arbitrary point, like right there. Happen to pick a point inside. Distance little r from the center. Think of that as point A. And then we'll go on out, break in scale, that's what that means, on out to point B at infinity, where by definition we will assign the electric potential value out there to be 0. And so our task will be to find the electric potential at point A, which we are just going to call V of little r. So we still just do the same thing. Delta V means V at point B minus V at point A, which is minus the integral from A to B of E dot dr. But point B is out at infinity, and we define the electric potential there to be 0. And so that's gone. And then those two negative signs on each side cancel. And I'll replace the expression V of A, V at A, with V of R. So what I have left is V of R equals the integral, with the lower limit now being the radial distance of point A, and the upper limit being at a radial distance of infinity. E dot ds. So then you would integrate along a path from A to B, out at infinity. And you would plug in, notice you're going to have to break it up into two regions, the integral, first from point A out to the surface of the sphere, and then use the electric field expression E1, and then from the surface of the sphere on out to infinity, all the way out, but for that you use E2. Okay? And when you're done, you'll have a result that depends on big Q and little r and big R. And you will have found the electric potential at any point inside the sphere with a reference point at infinity. And then you could do the calculation again, pick a point outside the sphere, like right there, and call that point A, and do the whole thing over again. Integrate from A to B, and you'd be able to solve for the electric potential for any exterior point with a reference point at infinity. That's a very powerful approach, okay? That is used a lot in more advanced work, so I just want you to kind of be aware of that. So that's my example problem, where you use knowledge for the electric field to find the potential difference between 2 points. And that's all for this video.